Hello, I'm Wojciech. I'm an associate professor at the University of Waterloo, and this is joint work with my master's student Nandi. The title of our work is Detectable Sequential Specifications for Recoverable Shared Objects. In this presentation, I'm going to first state a concrete problem related to detectability, and then I'll describe our solution. I will very briefly discuss our proof of concept prototype, and then I will conclude with a summary of the paper. Let's start by defining the problem. Why do we need detectability? Well, consider the following execution history over a recoverable read-write register. Two write operations are shown. The first one takes effect because it runs to completion, but the second one is interrupted by a crash failure. Upon recovering from this failure, the application thread does not know exactly what happened to this operation. In general, this thread will have two questions. One, did this operation take effect? And two, if it did take effect, what response, if any, did it produce? These questions cannot be answered easily by simply reading the state of the shared object, because it could have already been overwritten many times by other threads. Detectability was first mentioned in a DISC 2017 paper by Friedman, Herlihy, Marath, and Petrank. And it's defined as follows. A data structure provides detectable execution if it is possible to tell at the end of a recovery phase whether a specific operation was executed. The term recovery phase is specific to a style of recovery where threads are presumed to crash simultaneously. In other words, crashes are system-wide, and then recovery actions are performed in a single recovery process. When this process finishes these recovery actions, that's the end of the recovery phase, and this is when application threads are allowed to resume. In the PPOP 2018 follow-up paper, Friedman, Herlihy, Marath, and Petrank gave some additional details regarding the implementation of detectability, and they specify that a special announcement array is used to record both the intention of a thread to execute an operation and the result of that operation. This announcement array is shared between the application thread and the centralized recovery process. The general pattern is the following. The application first announces its intention to execute some operation op by writing to the announcement array, and then it executes op, and then a crash happens, and then in the recovery phase, the recovery process analyzes the state of the data structure and updates the announcement array as required. And finally, in step 5, when the application thread resumes, it can retrieve the result of the operation from the announcement array. At the outset of this project, we made it our goal not to reinvent detectability, but rather to formalize it. However, in the process of formalizing detectability, we also came up with some innovative ideas, which I will explain shortly. Several papers have been published recently in top venues on the topic of detectability. The first two papers introduce detectability and also present a detectable queue data structure. The third paper presents an alternative formal definition of detectability and also introduces a feature called nesting safety. The fourth paper presents additional detectable data structures, and the fifth paper discusses upper bounds and lower bounds on the space complexity of detectable objects. Next, I will describe our solution to the problem of formalizing detectability. Our methodology is based on the following three design goals. First of all, we would like to encapsulate detectability in an implementation-independent manner in the object's abstract interface. Our second design goal is that this abstract interface should be model agnostic. For example, to detect the outcome of some operation that was interrupted by a failure, the application thread should invoke a method on the detectable shared object rather than reading the result of that operation from some low-level concrete shared variable. The use of such shared variables ties the interface specifically to the shared memory model, whereas we would like the interface to be portable across shared memory models, message passing models, and hybrid models. Our third design goal is that this interface should be implementable on modern hardware. With respect to shared memory, this means implementable on current generation Intel systems with Optane persistent main memory. Our main contribution in this paper is the definition of a detectable sequential specification, or DSS. The DSS is obtained by an automatic transformation of the object's original sequential specification. Recall that the sequential specification of an object defines its correct behavior under sequential access, and it can be specified either as a set of legal sequential histories or as a set of states and possible state transitions. To define the correct behavior of a detectable shared object under concurrent access, we compose in a traditional manner the detectable sequential specification with an off-the-shelf linearizability-like correctness property, such as strict linearizability. The original sequential specification is transformed to the new detectable sequential specification as follows. Given an operation op in the SS, we create two auxiliary methods that are specific to op. Prep op is used to announce the intention to execute op detectably in the future. Exec op then executes op detectably. Then there's a third auxiliary method, which is not specific to any op, which simply tells us what was the most recently prepared operation and what was the result of this operation. And this is how we find out whether op actually took effect by way of this exec op, and if so, what response did it produce. And finally, we include op itself in the DSS, which allows the application to also execute op in a non-detectable manner. This way of defining the DSS has two fundamental advantages. One is backward compatibility. Anywhere you can use the original SS object, you can use its DSS counterpart because it provides the same operation op. And number two, detectability on demand. The application can choose to use costly detectable operations or more efficient non-detectable operations depending on its needs, and it can actually mix both styles of execution in the same execution history. In the paper, we formalize this transformation using an axiomatic style inspired by the Hurley, He, and Wing paper on linearizability, but due to lack of time, I'm going to skip this in the presentation. Here are some examples of the DSS in action in the context of a recoverable read-write register. In these examples, the application thread calls prep write 1, exec write 1. This is where the write 1 is actually applied to the shared register. Then after the crash, it calls resolve. Resolve returns a pair. The first element is the most recently prepared operation signature. The second element is the outcome of exec write. OK, indicating the write took effect and returned OK, or bottom, as in this case, indicating that exec write was either not invoked or it was invoked but did not take effect. And now a few words about our proof of concept prototype, which is a DSS-based detectable queue for the shared memory model with persistent main memory. Our algorithm is based on a durable queue of Friedman et al., which itself is a recoverable version of the well-known Michael and Scott queue, or MS queue. In this single-socket scalability experiment, we compare the original MS queue running on Intel Optane persistent memory to our DSS queue with non-detectable operations, to our DSS queue with detectable operations, which are slower, to the detectable log queue from the Friedman et al. Paper. Time's up. In summary, we introduced a new formal notion of detectability for shared objects, which has some interesting features. And we discussed a proof of concept prototype, which was tested using Intel Optane persistent main memory. Thank you very much. I look forward to your questions.